Hi everyone, I'm Bingchen Wang from Dr. Lily's group at the University of Pittsburgh. Today I would like to report our group's progress on on-demand treatment of wastewater using 3D printing membrane. The goal of our work is to demonstrate on-demand separation of multi-component and multi-phase water-oil mixtures using 3D printing membranes, with a focus on wastewater treatment and valorization. The achievements of our work so far is that we designed novel 3D printing membranes with multiple selectivity for liquid-liquid separation, and we have demonstrated improvements in energy efficiency, reduction in waste production, capital costs, and physical footprint of the plant using the 3D printing membranes. By demonstrating their values to our industry partner and by validating the developed technology, the project will provide a model for others in the chemical industry. For the details of our work's impact on industry, as we demonstrate the efficient separation and valorization of multi-component and multi-phase wastewater, we expect our work to be first of its kind demonstration of the concept for the chemical industry within the country. And compared with the conventional separation technologies, we anticipate at least a 20% increase in energy efficiency, at least doubling in energy productivity, and at least 20% reduction in waste using the 3D printed separation membrane. Conventionally, for membrane separation of three-component mixture, we can only achieve separation of one phase from the other two components. The separation of the other two components will usually require decanting or distillation processes. With our novel 3D printed separation membrane, we aim at separating all three components from each other in a single process. For our current work, in phase 1, we study the separation processes by varying pore sizes and materials, by manipulating the pore topography, and by applying supported ion liquid membrane to separate miscible liquids. Then we integrated all designs in a single device to separate liquid-liquid mixtures. In phase 2, we will have a given waste mixture, and we will perform on-demand design of various parameters of the integrated 3D membrane, and perform on-demand separation. Previously, successful oil-water separation has been demonstrated with hot water treatment of the 3D printing membrane. Our objective here is to make an intrinsically hydrophilic mechanical membrane, because it's not practical to use hot water treatment every time for oil-water separation. We found a sweeter ionic hydrogel recipe that includes SBMA as a sweeter ionic monomer, acrylamide as a comonomer, and MBA as a crosslinker. Our approach is to dip a 3D printed plastic membrane into the hydrogel solution and pull it out, and then place it under UV light where the hydrogel is in situ polymerized and attached onto the plastic membrane. Once the hydrogel completely solidified, the coating membrane was immersed in water. This allows the hydrogel to absorb water. The optical microscopy image confirms that a layer of hydrogel was coated on the membrane. Meanwhile, there's an open area for liquid to go through. The FTIR spectra further confirms the water absorption on the hydrogel coating membrane. The intensity of peak around 3400 inverse centimeter represents the hydrogen-oxygen stretching from water. The water peak was also strong after 31 times of oil-water separation, which demonstrates our hydrogel has the ability to hold water in the long run. It's also worth note that the 3D printed plastic membrane complements the weak strength of hydrogel underwater, so that the resulting membrane is mechanically strong. The figure on the left-hand side displays that we run 31 times of oil-water separation. We didn't need to run water treatment between the trials. For all the separations here, only water can pass through the hydrogel-coated 3D printed membrane, while oil cannot. Besides, the membrane kept a water flux level of around 350 liters per square meter per hour among all separation cycles. We didn't observe a decrease in flux. The flux recovery ratio maintained at 0.9 to 1.1 for all the tests. Combining the mechanical membrane and the supporting ion liquid membrane, Here we show our first generation integrated 3D printed membrane box design. The center box holds the feed mixture of benzene, heptane, and water, and 4 receiving side boxes allow benzene to diffuse across 4 supported ion liquid membranes. The 3D printed PMMA membrane is fed to the bottom of the center box to only allow water to pass through the membrane. In order to test the mechanical membrane with our first generation box, oils are dyed into red to differentiate from water. The results show that we have successfully demonstrated water separation through the 3D printed PMMA membrane. Both NMR and TGA results showed that the remaining mixture inside the center box contained less than 1% of water, and the water receiving side contained 99.5% of water. After the success of our mechanical membrane separation, we tested benzene separation with supported ion liquid membranes. 2 ion liquids were chosen to be impregnated into PVDF supporting material to test for benzene separation. With NMR analysis up to 24 hours, HMM-FAP showed better benzene separation compared to BMM-PF6 with 3.5 times faster flux rate. Even though we have successfully demonstrated benzene separation through our supported ion liquid membrane with HMM-FAP, the benzene flux rates for both ion liquids are too slow. Only 10% of initial benzene diffuse across the membrane, and the flux rate is at least 10 times slower than our target diffusion rate, so that the membrane side will need to be much larger to match industrial requirements. To solve the issue with our current supported ion liquid membrane, we came up with an approach to increase the ratio of surface area to volume for the integrated membrane box, so that we can have an increased total flux through the supporting ion liquid membrane. To test this approach, we have fabricated 3 types of cubes, 6 by 6 by 6, 3 by 3 by 3, and 2 by 2 by 2, only to test on benzene separation through supported ion liquid membrane. The parameters of area to volume on the table showed that we have achieved a comparison of 3 to 2 to 1. Our previous first generation integrated box has an overall size similar to the 6 by 6 by 6 cube in this case. The TGA results are shown on the right plot. Here, the smaller box with a higher area to volume ratio can increase the total benzene flux. The fastest benzene diffusion for this particular experiment was 50% benzene separation across supported ion liquid membrane. Since we confirmed this approach works very well, we can take the advantage of this idea to design our next generation integrated membrane box. For our previous oil-water separation system, we tested benzene separation from heptane and water. This is a 3-component, 2-phase mixture. Our membrane separation technologies do not only apply to benzene separation, but we can modify our membranes to become suitable for other components. Another example we have here is the wastewater treatment for Lubrisol's alcohol water system. This particular example is to separate 3 components from each other: methylpentanol, isopropanol, and water. Currently, the wastewater treatment is done by decanters and distillation columns. With our 3D printed membrane technologies, it is expected to reduce both energy costs and the footprint of the equipment. The most difficult challenge for this system is to get pure water, since water is miscible with IPA. To address this issue, we have added an additional step to include potassium carbonate salts to the system. Based on literature, potassium carbonate can ideally separate 90% of IPA from water because salts attract water molecules. Therefore, we have created a continuous system that included our mechanical and supporting ion liquid membranes. The mechanical membrane was used to separate the water-rich bottom phase. The supporting ion liquid membrane was used to separate pure NPL from IPA. We use glycerol as the impregnated solvent, since glycerol can act similarly to ionic liquids for the previous oil-water system. We also performed the techno-economic analysis using the model mixture of benzene, heptane, and water. For conventional approach, electricity is required for pumping a decanter, and heat is required for the distillation process. For our integrated 3D membrane, the separation is all gravity-driven. No external energy is required. Also, conventional system requires bigger equipments of decanter and column that take much more space, and the costs are likely to be significantly higher based on their sizes. In the future, for component level testing of the 3D printed membrane, we would like to study the separation of dilute solutions, which is highly desired in industry. First, we will demonstrate the separation of 1% dilute model solution using hydrophilic mechanical membrane. For the separation of supporting air liquid membrane, we will understand its thermodynamic limitations first, and we will demonstrate its separation of 1% dilute model solutions. Further, for integrated 3D membranes, we will demonstrate at least 90% separation efficiency at a flow of 1 gallon per minute. For alcohol-water mixtures, we will design the 3D membrane and demonstrate at least 80% purity at 1 gallon per meter. And we will optimize the integrated 3D membrane to demonstrate 99.8% purity of the desired stream. In summary, we have demonstrated 3D printed membrane is promising in separating multi-phase and multi-component liquid-liquid mixtures. We achieved almost 100% oil-water separation using hydrophilic 3D printed membranes. We showed that the supporting liquid membrane can efficiently separate miscible liquid-liquid mixtures. And we successfully performed on-demand separation of a given 3-component, 2-phase model liquid mixture using the integrated 3D printing membrane. We would like to acknowledge the financial support from Department of Energy, Rapid Institute, and thank you all for listening.